Next up, we're back to Rubin. Greg Daues will be giving us a talk about scaling production runs using HTCondor.
Thank you. Okay, I'll be continuing the discussion of Rubin Observatory. And it's very soon going to begin the legacy survey of space and time, 10-year survey. And so there'll be millions of images per year. And these data will flow from the summit at Chile, first to the United States Data Facility at SLAC, and then it will go to other data facilities in France and the UK. And we use a Rusio FTS-based system for that data replication. And as mentioned before, the project has different sort of flavors of processing. It's not all, HTCondor style. So there's real-time processing efforts, and those tend to occur in Kubernetes setups. There's also been some work using Panda at the European facilities. But for this talk, I'll be focusing on how we're using HTCondor. And with the HTCondor work, we certainly have been doing a lot of work with the data release production preparations. And that's been occurring at SLAC. But it's also important to sort of emphasize that with our HTCondor setup, we've had such a individual scientists and science teams have basically found the Condor setup to be sufficiently approachable and usable that they've been able to use it for some other very important work, such as the solar system objects and studying the adaptive optics system. And yesterday I heard about CPB, the collimated beam projector. I never heard of that before, but people were running Condor jobs studying the CPB. So it's provided, so it's been given us more than just a production system running on a service account. Individuals have been able to use it. And I think I've counted like over 50 to 100 users at the USDF who have been able to run Condor jobs in that setup. And so switching over to the data release production, it's a very large undertaking. It's going to require a lot of automation, a lot of things like automatic retries after failures. It's got all the pieces of a complex workflow, hundreds of tasks, hundreds of different data types, millions of jobs. So it's a big HTC problem. And the project is approaching this by sort of, small steps. So we're starting with data previews that are smaller in size than a fraction of the big problem. And we can kind of look at a picture of the whole workflow, and that looks kind of scary and formidable. But really, it's approachable as it's single-threaded jobs, and individual task types are embarrassingly parallel. So it's a very good fit for HTCondor. And so next, we just want to think, well, how do we begin to describe this workflow, for HTCondor? And we start that by using some Rubin-specific sort of constructs. And so these are sort of independent of any particular workflow management system. So we have like an individual quantum node that has a description of the task to be run and a unit of data. And then we make a whole quantum graph, the full, DAG of all those quantum nodes. And so with this, now users, we have to think, how do users actually begin to submit work? And the way they do that is they use one of the project software projects called the Batch Processing Service, or BPS. And so BPS serves as this layer between the user, the Rubin middleware, and finally the workflow management system, that we are going to use. And so it can support several different workflow management systems. And the heaviest lifting, say that BPS does, usually involves this quantum graph. So it first has to build this quantum graph based on inputs, such as the tasks to run and the input data collection. And that can be fairly time consuming. So it's kind of like can be a fairly long serial step at the beginning. And then after that, BPS can take that quantum graph and turn that into a real DAGman workflow to run. And in order to run that workflow, BPS sort of supports these various high-level actions. And so these are kind of like convenient. So a user just has to know these actions. They don't have to know, they don't have to find the Condor DAGman process and say, Condor hold or Condor remove or Condor release. So users can just work with the BPS constructs. But finally, after a BPS submit, we have a Condor DAG in the queue. So we have a DAG in the queue, but we're working. So this work is starting at the United States Data Facility at SLAC. And there we have a Slurm cluster provided by the facility. And so we don't have a Condor pool. So we do get some help in using Condor, that we do have some SCEDs and a collector that are run administratively on some login devel nodes that we have. And then from there, the approach we take is that we have individual users sort of generate their own Condor pool in the Slurm cluster. And so we have a utility that we call allocate nodes. And so users use allocate nodes to sort of create their Condor pool. And so in a simplest form, you can just say, well, give me 10 glidins, and I'll take 32 core glidins, and I want a particular Slurm partition. And then you specify what platform you're targeting, and then from that platform label, allocate nodes looks up configurations, and then it knows what to do. And so allocate nodes in this case will submit the Slurm jobs to the cluster. And the way this works is then the glidins run as the user, and they only accept the user's jobs. So they have a start condition that's pinned to the user. And so this approach kind of has a little bit of a barrier in that a user is, they're submitting the workflow on one hand, and then they're allocating nodes, over in another shell. And so if they want to avoid that, the BPS middleware will allow you to run the allocate nodes within a provisioner node. So DAGman has a provisioner node that runs alongside a running DAG. So, so you can make use, if you don't want to bother with managing allocate nodes yourself, you can just have it run in the provisioner node. And a little more detail, allocate nodes can run in sort of an automatic mode where rather than you having to specify how many resources you want, it will just check the Condor queue and react to the job pressure that it finds. So it'll submit the glidins that you need. And generally, it makes kind of generic, say 32 core glidins, but then if you have a large job, then it'll make a special glidin for that job. And we also have the ability to support what we call node sets. And so this is if you want to have dedicated glidins for a particular activity. Like we use this on our service account, that we'll want to assign some glidins just for the daily processing. And so we want to sort of have those run in its own set, whereas other processing can run in another set. And this is then affected by labeling the nodes with an add and setting up a start condition so that only jobs that have that label start in those glidins. And so this has been helpful for sort of dividing work, and so you can submit work with kind of like a very good idea of when it will finish, because other things don't interfere with it. Okay, and so with the previous tools, we have a DAG, and we have some glidins to run against, and so now we have to think of how do we configure the system for Rubin workflows. And the Rubin workflows are characterized by a very large number of short jobs. And so we've done a lot of tuning for this scenario. And one of the sort of situations that we observe with DAGman and short jobs is that you can reach situations where there's many jobs in a ready state, but the number of idle or pending jobs is too low. And so we have some settings that try to improve that situation. And by raising the value of DAGman max jobs idle, we're trying to allow Condor to sort of hold more idle jobs in memory. And with DAGman aggressive submit, we're trying to get DAGman to not exit submit cycles, too early. And so we're still studying those settings to see if they're doing what we want, but so far it's been kind of the proof of the pudding is in the eating. It's worked so far. So but we're still looking at that. And then after we get past that first problem, if we now have a lot of idle jobs and we want those to run fast, we found that we can optimize a little there too. Because we have the situation of user glidins, where there's really no competition, that no other user can run in a given set of glidins, so we can just tell the negotiator to ignore user priorities and to not consider preemptions. And we've actually seen that does make a significant difference, that we were seeing the negotiator stopping our big workflows from submitting jobs because of fair share considerations, which we're not interested in. And then, but there's more ideas that we might need to think about for the short jobs, and those can be in the area of clustering. We do currently support clustering of jobs to make the jobs longer, but that is unattractive in various ways, because if you make a sort of aggregate job and then you have certain failures, then you're not getting an atomic failure and retry capability. You'll have to rerun more jobs. And it also just sets up a scenario where your scientist who is worried about the adaptive optic system is now stopping and trying to figure out how to take short Condor jobs and make long Condor jobs. And so we just want to avoid that whole situation. And so we are talking to the Condor team to see if they can look at having Condor do clustering internally. And so we look forward to any sort of progress that can be made in that direction. And we also have problems with reporting status of large DAGs, that the way you check the status of a DAG is by reading a node status file, and that's a very big file, and it's very slow. And there's also some DAGman class adds, but for a large DAG, those numbers are sort of getting very large and are not very convenient to work with. And so we are talking to the Condor team about possibilities where these reporting mechanisms for the DAG might be able to sort of be separated into categories. And we would like it if It could be like for, like we kind of have a favorite class ed that that in a Rubin workflow, the task of a job is labeled with a, say, BPS job label. And so if we could get more for the finer grain DAG reporting for jobs of different types, that would help people, that would help the cause a lot. Another item is that in our DAGs, we have situations where we'll want to run jobs in a particular order, but we do not want the failure of an early job to block the future execution of one of the next jobs. And so we don't want we want an ordering, but we don't want a rigid dependence. And so this is something that is not yet really in DAGman. And so we kind of jump through some hoops to make things work. But we're talking to the Condor team to investigate the idea then of this weak dependence. So if they can put into DAGman the contents of a weak dependence where a job precedes other jobs but does not block upon failure. Okay, so those are kind of some of our concerns, and I can kind of summarize then. So for the work at the USDF, we're working with our BPS plus HTCondor. We're allocating nodes. We're doing all the processing. It's all internal to the Slack site. We can keep 10,000 cores busy for a long time, and so that's good. And our sort of practice for the data release processing has been this data preview 2 campaign. And we've been running that over a period of 40 to 50 days. And it's made a lot of progress and nearing completion. And all of the Condor class set information is being loaded into OpenSearch that we can use to study this campaign. And then to kind of extend upon what we have done so far, we're now looking at the ability to run Condor jobs at the other data facilities. And our base scenario for doing this is to have the USDF at Slack to be the home base, to be the point where all the workflows are initiated. And then just and then glidins can join in from the other facilities. And so what we do is we run a Condor collector and a sked, and we run that in Kubernetes so that we can set it up to be reachable through the firewalls. And then we sort of extend allocate nodes to work with different platforms where it no longer just submits to a Slurm scheduler, but it creates grid universe ARC jobs, and those jobs will be submitted to the ARC-CE service that is like the border service for the facilities. So we're working with this idea, and so we've been doing some testing with this, and the glidins do start at the remote sites, and they join our collector in Kubernetes. And we kind of organize these things with our node set attribute that we label. The France glidins are labeled with a French DF label, and so jobs can be targeted to the France side using the appropriate node set label. And so we've started test runs at all 3 facilities. Those are the French DF at CCI and 2P3, and Lancaster and RAL. And this sort of capability to have users at USDF kind of throw stuff against French DF, that's kind of helped us study the data situation a bit more, that we're studying now the caching configurations. Like at CCI and 2P3, the data storage is the Dcache system, and our pipelines can set up a caching environment per glide-in, and so we get essentially data staging. You know, the more cache hits you get, the better you're doing as far as like effective data staging. And so we've now sort of opened the door that we can now start looking at these, trying to utilize these remote sites in an efficient way. So I can stop there.
Thank you, Greg. It's like TJ is first.
Yeah, so you mentioned in an earlier slide something you called clustering of jobs. Is that a single DAG node with multiple jobs in it? Or is that you packing multiple tasks into a single Condor job?
Yeah, that's 10 tasks into one Condor job.
Okay, love to have a discussion with you about maybe making that more seamless. I have some thoughts.
Yeah, so on that topic, one thought I had is on the clustering, maybe that node in the DAG could be a job list, you know, of submit file with, you know, Q10 or Q50 or whatever it is. And you know, instead of one job where you have all these jobs behind the scenes and then it's hard to know what happened to each individual step, maybe a node in your DAG could be, you know, a job list or, you know, job cluster.
Like a cluster?
Yeah, exactly. Exactly. And then your Elasticsearch would still have an individual job ad for every job. Your the SCED would see all those jobs.
You would still get, you know, if detector 17 failed, I would still retry and detector 7, and it wouldn't affect anything else. So yeah.
Yeah. So that's an idea for the clustering. I had a comment too on I think it was slide 5. By the way, I loved your talk. Slide 5, I think it was. Slide 4. Slide. Yes, right here. Yeah. It says they are embarrassingly paralyzable. Nothing is embarrassing about it. It's pleasantly paralyzed. Right? It's wonderfully parallel.
Wonderfully parallel.
Wonderfully parallel. It's perfectly parallel by design. Yes. And then on your running SCEDs inside of Kubernetes with glide-ins, we've been doing some work on that ourselves. And you might want to talk at a break with Matt Westfall. He can wave at you. But when combined with CC, we've done things like, okay, you're running a SCED in Kubernetes. It's using CCB to talk to execution points behind firewalls. You know, what happens if that pod is killed and restarted? What happens if the TCP ingress on your Kubernetes cluster dies and is restarted? And we've made some discoveries and workarounds. So you might, you know.
Yeah, I think we'll have to do some work there. Like right now, if my pod restarts, all my ID tokens are useless.
We can help.
So we got to do something. Yeah.
We've done work on figuring out all the different Condor system directories you need to persist between reboots. We can definitely talk about that. Yeah.
So we actually have done work on clustering inside jobs with the Condor team or parts of the Condor team. So maybe we should chat about how we did that, because it's outside of Condor in some respects. We're using a message queue to accumulate the work. And then the pilot basically says, I need work, and grabs it from the message queue. And that is kind of, I mean, instead of sort of getting out the Condor hammer, you have some sort of secondary thing that runs on the side, sort of as a workflow manager, especially when you have lots of tiny little jobs, like that are like seconds, minutes, etc. That has been really efficient for us in IceCube. So we can chat about that with the Condor team as well.
I got a quick thing. Thank you for the reminder / list of Dagman stuff I need to work on. But I was curious, you mentioned you're using provisioner nodes. Have you had any woes with using those, or have they been working fine for you?
The provisioner, I don't think there's been any. Don't think we've had any problems with the provisioner. I guess maybe there's one or two scenarios, or one or two times where maybe I can't remember whether it exited or didn't exit, or but really it's been pretty solid.
So you talk about glide-ins a lot, so I'm wondering if you're using glide-in WMS, or this is like you re-implement part of that layer, or if this is all part of Condor. That's something I don't understand very well.
I mean, I'm not an expert at glide-in WMS, but my general sense is that glide-in WMS is a bit more of a institutional investment. Kind of like you kind of have to throw more resources at it. And maybe like people on site have to like really like, in some sense, it would have been great if Fermilab and Slack like all used like the same things and all got together and did that. But I have a user account at Slack, so I don't.
So I mean,
I can only do so much.
Technically you could have a Rubin front end to glide-in WMS, quote unquote. I don't know how sustainable that is from the Fermilab side, because it's one more thing. It's one more thing. And there's only, I guess, 2 or 3 sites, a handful of sites.
Yeah, there's 3 sites where the UK is 2 sites. So you can call it 4 sites if you want.
So this feels a little bit like the gliding WMS hammer coming down and everything looking like a nail. This is running the infrastructure, et cetera. It's a question about funding at that point. This might be easier with like literally a shell script that talks off the CE.
Okay. Oh, one more. If our next speaker is Sungjin, can you come down and we'll get you going, and then Brian, right? Yeah.
Hi, yeah, this is Liz Sexton Kennedy from Fermilab and CMS. And I would agree with that, CMS has hundreds of sites that it has to submit to, not 3. And so we really need the full hammer of the gliding WMS that we support. It sounds like you're doing fine with what you got, but if Rubin ever like pushes out to, hundreds of sites, then we should probably think about collaborating.
Yeah. Marone is, always saying that you're going to need more capacity someday. So,
you get
he could be right, and so
right.
we will see.
You get 50 petabytes per year, right? And you're going to run for 10 years. So it could get to the point where, in the far future, you really need some large federation of sites like CMS needs.
All right, thank you.